researchers have uncovered an astonishing discovery deep within these cosmic entities. At the core of these ancient celestial beings, they've unearthed something both awe-inspiring and chilling within a black hole, challenging all previously held beliefs about these cosmic marvels. Prepare yourself as we unveil the captivating mysteries concealed in the heart of a black hole. If you want to stay informed about the latest developments from the universe and its surroundings, don't forget to subscribe to our channel, like 30 seconds this video, share it with others so it reaches a broader audience, and hit the notification bell. Black holes have always been a captivating subject, as theorized by the brilliant physicist Albert Einstein in his general theory of relativity. According to this theory, the gravitational force at a black hole surface is so immense that not even light can break free. Gravity doesn't act like traditional forces such as magnetism, which push and pull. Rather, it's a consequence of the warping of spacetime. Essentially, gravity originates from how 1 minute and 3 seconds mass and energy cause the fabric of spacetime to curve. The curvature of spacetime mentioned earlier is what we refer to as the gravitational field. The greater the energy of an object, the more intense its gravitational field and the more pronounced the spacetime distortion. Now, let's delve into black holes, one of the most extreme phenomena in the cosmos. These objects contain unimaginable quantities of mass and energy packed into an incredibly small space. Due to their tremendous mass, the gravitational 1 minute and 36 seconds field of a black hole becomes extraordinarily powerful, creating a profound warp in the spacetime continuum. This is where things start to get truly extraordinary. The gravitational pull near a black hole is so overwhelming that it forms what's called an event horizon. This event horizon isn't a physical wall but a region where space gradually bends, forming an invisible boundary, a point of no return. Once something, whether it's a spacecraft or even light, crosses this threshold, it can never escape the black hole's grasp. 2 minutes and 9 seconds, the event horizon acts like an invisible force field, trapping everything within it, including light, which is normally considered the fastest entity in the universe. To emphasize just how extraordinary this phenomenon is, imagine turning on a flashlight. The light rays travel at an astonishing speed of around 300,000 kilometers per second. However, if you found yourself inside a black hole, the speed needed to escape its pull would exceed the speed of light, something that's currently deemed impossible according to modern physics. At the core, 2 minutes and 43 seconds of a black hole, we encounter what's known as the singularity. This is where all the mass and energy of the black hole, no matter how immense, gets condensed into an infinitesimally small point. The singularity is like a giant cosmic entity with a gravitational force and curvature that are beyond comprehension. In fact, the singularity possesses infinite gravity and curvature, which is a truly fascinating concept. When attempting to understand the singularity, our current understanding of physics breaks down. We don't have a 3 minutes and 15 seconds clear idea of what occurs there, almost as if the laws governing our universe take a hiatus or vanish altogether, leaving us completely bewildered. Scientists are continuing to explore this enigmatic region in hopes of unraveling the secrets hidden deep within black holes. To comprehend the formation of black holes and what transpires within them, it's essential to examine the life cycle of massive stars. These massive stars are true cosmic powerhouses, driven by intense nuclear fusion reactions occurring in 3 minutes and 46 seconds their cores. Their energy comes from the fusion of hydrogen and helium. During this process, 2 hydrogen atoms collide and merge to form a helium atom. As long as the star has sufficient hydrogen to fuel the fusion process, it can sustain its brightness. However, stars have an insatiable appetite and continually push to keep the fusion process going. When the hydrogen in the star's core gets exhausted, the star gets creative and starts fusing heavier elements such as helium, carbon, and oxygen. Each subsequent 4 minutes and 20 seconds fusion reaction produces less energy than the previous one. To make up for this energy loss, the star has to work harder, burning fuel at an increased rate and raising its internal heat to maintain its delicate equilibrium. Eventually, a critical point is reached where the star can no longer fuse any more elements. At this moment, the star collapses under its own gravity in a spectacular implosion. It is during this collapse that a black hole is born, and the core that's left behind becomes the heart of the black hole, known as the 4 minutes and 53 seconds singularity. Recently, scientists directed their cutting-edge telescopes toward the interior of a supermassive black hole located in the heart of a galaxy approximately 800 million light-years away. Black holes are notorious for their insatiable hunger, devouring anything that ventures too close. In this case, the black hole's cosmic feast was truly remarkable. As matter fell into the black hole, it was heated to incredibly high temperatures, reaching millions of degrees. The scorching gas produced a 5 minutes and 25 seconds glowing corona around the black hole, forming an intense cosmic halo. The resulting X-ray flares, akin to cosmic fireworks generated by the superheated gas, didn't vanish into the abyss of the black hole. Instead, they experienced an unusual cosmic bounce. These flares reflected off the gas behind the black hole, defying the laws of physics as they encountered the black hole's powerful magnetic and gravitational fields. Remarkably, they survived the black hole's gravity and magnetic fields, which bent the X-ray flares, sending them on a curved 6 minutes and 1 second trajectory that ultimately reached our telescopes. This groundbreaking discovery marks the first direct observation of light emanating from inside a black hole, providing additional confirmation of Albert Einstein's theory of general relativity, which predicted that gravity could bend light. This observation validates Einstein's foresight, reaffirming the brilliance of his groundbreaking ideas. But how did this remarkable discovery come to light? The story revolves around two impressive space telescopes, the European Space 6 minutes and 32 seconds agencies XMM Newton and NASA's James Webb Space Telescope. These telescopes were focused on a supermassive black hole and observed quite a spectacle. Over several days, they recorded fascinating X-ray flares emitted by the superheated corona surrounding the black hole. However, things took an intriguing turn when researchers delved deeper into the data and noticed something unusual. Some of the flares had distinct colors and arrived later than others. This raised a new question. Why did some flares arrive later and display 7 minutes and 5 seconds different colors? Eventually, it was revealed that these X-ray signals originated from within the black hole itself. This unexpected observation prompted the researchers to conduct a thorough analysis using complex cosmic calculations. As they pieced the data together, an extraordinary phenomenon emerged, a phenomenon known as a light echo. As we know, black holes exert an extremely powerful gravitational force, so intense that even light cannot escape. However, in the vicinity of a black hole, one often finds a swirling disk of 7 minutes and 39 seconds material, such as gas or dust, drawn in by its immense gravity. This material heats up as it spirals inward, emitting X-rays and other forms of radiation, creating a glowing ring known as the corona. What are your thoughts on this discovery? Let us know in the comments section. If you enjoyed this video, don't forget to hit the like button and subscribe to stay updated on similar content. Thank you so much for watching, and we'll see you in the next video. The intriguing nature of black holes lies in their ability to bend the very fabric of space and time. This bending isn't just a theoretical concept, but a reality confirmed through various astronomical observations and scientific advancements. Recent breakthroughs in black hole research show just how little we truly understand about these cosmic giants. Even though we now know a great deal about how black holes behave on a large scale, their core mysteries remain largely unsolved. The curiosity surrounding the singularity at the center of a black hole grows stronger. 8 minutes and 41 seconds each day. The singularity represents a point of infinite density, where the gravitational force becomes so strong that space and time themselves cease to behave in any recognizable way. This presents an intriguing paradox for physicists. The laws of physics that govern our understanding of the universe simply do not seem to apply under the extreme conditions of a singularity. This is one of the biggest puzzles in theoretical physics, as it suggests that our current models, particularly those that combine quantum mechanics and 9 minutes and 11 seconds general relativity, may be incomplete. One of the most significant aspects of black holes is their profound effect on surrounding spacetime. This effect, often referred to as gravitational time dilation, means that time moves differently depending on how close you are to a black hole. The closer you are to the event horizon, the slower time appears to pass relative to an observer farther away. This effect has been proven by observing objects near black holes and studying how time behaves around them. For example, satellites orbiting 9 minutes and 43 seconds Earth experience a slight difference in the passage of time compared to objects on the planet's surface due to Earth's gravity. However, the effects near a black hole would be far more extreme. The discovery of light echoes, as mentioned earlier, is an extraordinary step in confirming theories about how black holes interact with their surroundings. Light echoes occur when light bounces off objects surrounding a black hole, particularly those in the accretion disk, the spinning, glowing mass of gas and debris being pulled into the black hole. 10 minutes and 13 seconds. This phenomenon is analogous to echoes of sound that bounce off surfaces in our environment. However, these light echoes offer crucial insights into what's happening in the black hole's immediate vicinity. By studying the timing, color, and behavior of these echoes, scientists can infer properties of the black hole that were once unimaginable. Furthermore, the study of supermassive black holes, which reside at the centers of most galaxies, is becoming increasingly important in understanding the formation and evolution of galaxies themselves. These black holes often hold the key to understanding why galaxies take the shapes they do, how they evolve over time, and why some galaxies, like our Milky Way, seem to harbor such massive cosmic objects at their centers. 10 minutes and 44 seconds. In fact, the supermassive black hole at the heart of our galaxy, Sagittarius A*, has been the subject of many observations. Despite being millions of times more massive than the Sun, this black hole has only a modest influence on the Milky Way compared to the way smaller black holes affect their surroundings. As scientists continue to refine their understanding of these colossal objects, new questions arise. How did these supermassive black holes form? Did they come into existence from the collapse of massive stars, or could there be other processes at play? 11 minutes and 13 seconds. Some theories suggest that these supermassive black holes could be the remnants of primordial black holes, objects thought to have formed just after the Big Bang. Others propose that they may have grown by slowly accumulating matter over billions of years, starting from smaller black holes. The immense gravitational force of black holes also leads to a phenomenon known as spaghettification. This occurs when an object moves closer to a black hole, and the difference in gravitational force between the near and far sides of the object stretches it to an extreme degree, much like spaghetti. 12 minutes and 12 seconds. While this might sound like science fiction, it's a very real process that happens in the extreme environments around black holes. The study of black holes is not just a scientific pursuit, but also a philosophical one. They raise profound questions about the nature of reality, the limits of human knowledge, and the very fabric of the universe. How can we comprehend an entity that warps time and space? What happens beyond the event horizon? Can we ever truly know? These questions challenge us to rethink our understanding of the universe at the most fundamental level. In the future, as new technologies and more powerful telescopes are developed, it's likely, 12 minutes and 46 seconds, that our understanding of black holes will continue to evolve. The Event Horizon Telescope, for instance, made history by capturing the first-ever image of a black hole shadow in 2019, offering a glimpse of the giant black hole at the center of the galaxy M87. As these advancements unfold, we may uncover even more mysteries that challenge everything we thought we knew about the cosmos. As researchers continue to explore the immense depths of space, the role of black holes in the universe will remain one of the most 13 minutes and 19 seconds captivating and mysterious phenomena in all of science. Their study not only pushes the boundaries of our understanding, but also reminds us of how much there still is to learn about the universe we inhabit. Each discovery brings us one step closer to understanding the true nature of black holes and the incredible forces that govern the universe. One of the most thought-provoking aspects of black holes is their potential connection to the fundamental nature of space and time. Black holes represent a boundary where 13 minutes and 48 seconds our understanding of classical physics, like Newtonian mechanics, and quantum physics come into direct conflict.